Okay, example 18.7, liquid support. Okay, so we've got this setup over here. It looks a lot more complicated than it is. Very simple to answer this question. Okay, so what is the question? Well, first of all, we have a tank over here. Okay, it's open to atmosphere, and you've got water over here. Then you've got a very light movable partition. Okay, so this can move up and down, but it separates water from oil. And then in this container here, we've got oil, and goes through this pipe into this also this little container over here with a, this is important, with a piston on it. Okay, alright, so you've got this whole setup over here, water, oil, and you have this piston that is resting on it. Okay, if the piston in the bottom tank is 1/2 meter below the open surface of the water, okay, 1/2 meter below the open surface of the water, and it has a surface area of 8.3 times 10 to the minus 3 meters squared, what must the mass be of the piston to keep this system in equilibrium, mechanical equilibrium? Okay, so what's happening is that you've got this pressure, this atmospheric pressure pressing down on the water, and you've got this pressure drop, not pressure drop, pressure increase as you go down, okay, and then you've got another pressure increase, and so there's this increase in pressure, and it's pushing on this piston. This pressure is pushing the piston up. But what must the mass be so that the mass of the piston will cause gravity to pull down with basically the equivalent force, so that this thing is in equilibrium? Okay, so how do we do this? Well, let's begin with this piston and say, well, if we assume that this piston is in equilibrium, then we draw a free body diagram. Well, we draw a free body diagram anyway, but it's in equilibrium. And what are the forces acting on this piston? Well, we've got the upward force of the pressure in this oil that's pressing up, right? There's pressure in the oil pressing up, and this is applying a force, an upward force. Okay? And then you've also got gravity pulling it down, right there. Force of gravity pulling the piston down, and you've got atmospheric pressure, the pressure of the atmosphere being applied also down on the piston. I hope that makes sense. You've got those three forces. Okay. Now remember, the question was, what does the mass of this piston need to be so that this whole system is in equilibrium? Okay. So if you rearrange the forces, okay, so we've got upwards, we've got the force of the oil on the piston, minus the force of atmosphere pressing down on the piston, and minus the force of gravity acting down. Okay, but we need to write these in terms of the pressures. So what is the force of the oil? What is that force of the oil being applied to the piston from the bottom? It's equal to the pressure in the oil times the area of the piston. Okay, remember, force is pressure times area. Okay, so that's what that is. Minus the force of the air pressure, which is simply the pressure of the air, the atmosphere, times the area of the piston. And then what is the force of gravity? That's simply the mass of the piston times gravity. And you can solve for the mass of the piston by rearranging those things. Okay, so that's step one. Step one is to get the mass of the piston in terms of the atmospheric pressure and the pressure in the oil. Okay, over there, which is P3. Okay. Alright, so now what is P3? That seems to be the key here. We need to find what is the pressure there in the oil. And so the way that we do it is we say, okay, well, let's relate this pressure back to a higher point using these equations. Recall, the pressure at a deeper point is equal to the pressure at a higher point plus rho g h. Okay, let's try to use that guy. See how we get, where we get from it. So pressure 2, let's just see if I can move this up a bit. Okay, pressure 2, how does pressure 2 relate to pressure 1? How does pressure 2 relate to pressure 1? And how does pressure 3 relate to pressure 2? Okay, that's what we're going to do. So pressure 2 is equal to pressure 1 plus density of water G D1. Okay, where D1 is the difference between point 1 and point 2. That's D1, right? And what is pressure? What was the pressure there? It was the atmospheric pressure, which is pressure in the air, plus the density of water GD1. Okay, I think that's pretty straightforward. Now, what about between point 2 and point 3? Okay, it's going point 3. Pressure 3 is going to be the pressure at 2 plus rho GD, but it has to be the rho of oil, the density of oil, G, times that difference, right? That D2. Okay, so we've related point 2 to point 1, and we've related point 3 to point 2. That's what we've done there. So we've got point 2, point 3. And this point 2 we just saw was this. So we take this and we substitute it into this point 2, and we get point 3 equals this quantity here. Okay, so now we can take that point 3, which is this, and substitute it into here. Let me just quickly see what it was. So the mass of the piston is pressure 3 minus pressure of the air multiplied by the area of the piston divided by gravity. So P3 was this guy. We plug that in, minus the air pressure times the area of the piston. Okay, and you multiply out and you get this mass over here. Alright, I think that's pretty straightforward. Okay, it would be good if you could also read through this, evaluate the result, and see if you understand. Okay, cheers.